Good afternoon, everyone. So I wanted to let you know that I'm not an engineer. I'm not a technologist. I'm a planetary atmospheric modeler. But what I want to talk to you all about today is really an opportunity. It's an opportunity for low-hanging essential science that can be done from geosync orbit, can be done from the moon, or can be done with interplanetary spacecraft. So as many of you might know, the Astronomy and Astrophysics 2020 Decadal Survey included within it many recommendations, but alongside a recommendation for a technology maturation program for great observatories, often referred to as GOMAP, the top recommendation for a flagship level space-based mission was for an observatory at roughly the 6.5 meter, primary scale. That would be capable of doing direct imaging of exoplanets in reflected light with sensitivities that could get it down to observing Earth-like exoplanets in the habitable zones of nearby stars. And so the idea behind this mission, or the motivation behind this mission, would be to collect a sample of about 25, you can see the tilde 25 there in the slide, of these exo-Earth candidates such that we would have a statistical sample of worlds that could be like our own. Spectroscopy would be included so that we could survey them or understand them in greater detail, and we could start to understand whether or not planets like our Earth are common or uncommon in the nearby galaxy. Now, what I find particularly motivating about this mission, whose name has recently, that's kind of stuck, is called the Habitable Worlds Observatory. What I find particularly motivating about this mission is the engineering challenges that it incorporates, as well as the diverse fields of science that come to bat for this concept or for this mission. So this is a simulated image of what a telescope like this could deliver. This was for the HABEX concept, which was a mission concept that fed into the Decadal Survey. This mission concept was also focused on direct imaging of Earth-like exoplanets around nearby stars. And so what you can see in this simulated image is a planetary system with a debris disk analogous to our own Kuiper belt in the outer reaches of this planetary system. The planets are all indicated there with little letters, but they're sometimes hard to spot. And then, do we have a laser pointer? Actually, use the mouse. Okay. So at the largest scales, at extragalactic scales, what's important for a direct imaging mission like this are there going to be background sources of light that literally come to light during the deep stares that we have to do to detect the faint planets in these exoplanet systems. Also, an astrophysical target are the planetary debris disks that are going to be present in these systems. So we need to understand something about the occurrence rates of these debris disks, their distributions and how thick they are for us to prepare for a mission like Habitable Worlds Observatory. Of course, the targets in these systems are planets themselves. And so we're going to need good planetary science to be able to prepare for Habitable Worlds Observatory and to be able to interpret observations that come back from Habitable Worlds Observatory. And so what I'm showing you here are modeled spectra of potential targets for this mission. This helps to highlight that the wavelength range that we're going after here is going to be something like ultraviolet, visible, and near infrared. And the kind of resolutions that we're talking about here are moderate by the standards of astronomers and planetary scientists to low by some standards. And then, of course, the needle in the haystack, as it were, that a mission like this is going to go after are the potential exo-Earths. And so we have a pale blue dot sitting down here in the lower right. Now, in the Decadal Survey, where this image was actually taken from, and throughout the Decadal Survey, there are numerous spectra of Earth that appear, but those are not actual data for our planet. Those are all based on models. You might be surprised to know, and I will demonstrate this a little bit later in the presentation, that over the wavelength range that we care about for Habitable Worlds Observatory, there are some wavelengths and some phase angles for our planet where we don't actually have spectroscopic observations of the brightness of our world. You may also be surprised to know that in standard publications and in standard tables for things as simple as the visual geometric albedo for our planet, so that's the full phase reflectivity of our planet, commonly adopted values for that are off by about a factor of 2 for our Earth, which is really shocking given that we live on this planet and maybe should understand it a little bit better than that. But of course, the challenge with understanding the world that we inhabit is with perspective. And so our local horizon does not reach the entire planetary disk. You care about the entire planetary disk because with a mission like Habitable Worlds Observatory, they see their targets as point sources. And so that is an entire planetary disk that has been integrated down into a single point of light. And so you actually have to get pretty far above Earth's surface before you can start to see the curvature of the Earth, and more importantly, to be able to see the entire disk for Earth to then stand in as an analog for the kinds of targets that Habitable Worlds Observatory would image. So on this slide are represents where the horizon would reach at different altitudes above Earth's surface. So in kilometers, so at 10 kilometers where airliners might fly, 40 kilometers where high altitude balloons head up to, 150 kilometers, which are sounding rockets, 410 kilometers is the International Space Station. If you go to 2,000 kilometers, that's kind of the upper limits of low Earth orbit. And so even at the upper extent of low Earth orbit, your horizon just isn't big enough to glimpse the entire disk of our planet. If you go to geosync, 36,000 kilometers indicated on there, you get about 97% of Earth's entire disk, which is sufficient. It's not great, but sufficient for the kinds of science that you would want to do to prepare for Habitable Worlds Observatory. Certainly, if you go beyond that, if you go to the moon, at the moon you capture 99.9% of Earth's disk, and if you go to interplanetary spacecraft, you do even better. So some challenges with low Earth orbit are that it does not view the entire disk of Earth from its vantage. It's also not viewing, if you're talking about a single spacecraft, it's not viewing every location on Earth at the same time as you would for an exoplanet. There are also some issues with the way the spacecraft is pointed. Generally, spacecraft at low Earth orbit are pointed at nadir. When you're thinking about the entire disk of a planet, only the sub-observer point is at nadir, and then around to the limbs of the planet, you're now looking at those through slant paths through the atmosphere. Again, you can go to geosync and get most of Earth's disk, but for the kinds of spacecraft that tend to go to geosync, which are very important for climate predictions and climate understanding for Earth scientists on our planet, they have a finely tailored set of filters that they kind of standard launch on these spacecraft that go to geosync. And so, for example, kind of the most advanced spacecraft that we have, NASA spacecraft that we have right now at geosync is GOES 18. And it spans 400 nanometers to 1.6 microns with just 5 filters, which is the entire wavelength range over which we would have spectroscopy for something like Habitable Worlds Observatory. You might be thinking about a certain trick that we can employ from the surface of our planet, which relies on Earthshine. So this is light that reflects off of our Earth, heads to the moon, reflects off the portion of the moon that is not illuminated by the sun, and comes back to Earth. And so that is sensitive to the Earth's reflectivity. But there are a number of challenges with using Earthshine observations as a stand-in when you're trying to design a spacecraft mission. So on the pro side, it does glimpse Earth's entire disk. It can be geographically biased, and that if you're repeating these observations from the same observatory here on Earth, you're only observing that one hemisphere that's accessible from where that observatory is sitting. It has yielded calibrated measures of Earth's brightness in a photometric sense, and that took a huge amount of work to get those to be accurate and calibrated. But there are major hurdles that are present in Earthshine observations when you want to do this spectroscopically. Again, Habitable Worlds Observatory is going to be taking spectra, and so if you want to design HWO, or when it comes time to execute HWO, if you want good data for what our Earth looks like as a function of phase and as a function of wavelength, this is an unsolved challenge for Earthshine observations. So then the obvious next place to go to, if you care about observing our planet as a stand-in for an exoplanet, is to go to interplanetary spacecraft, because they do glimpse the entire disk of our planet. And in fact, if they glimpse our Earth from afar and our Earth is encapsulated in a single pixel for that spacecraft, it doesn't matter for the purposes of exoplanet preparation studies. If they do resolve the disk, that's also fine, because you can just integrate the spatial information away on the disk. This has only been, I'll say, planned and followed through with great purpose on about 5 occasions. So in the upper left, in the lower right here was the 1990 Galileo flyby of our planet. And upper left is 1992, another Galileo flyby for our planet. Let's see, central here is NASA's epoxy mission, which was in the late 2000s. L-Cross at the moon looked back at our Earth on a few occasions in the early 2010s, and then the ongoing Discover mission, which is at Earth-Sun L1, viewing essentially the full disk Earth. And so exoplanet-themed publications have come from all of those studies at this point. But there are some challenges here. And so what I want to highlight is this is a table where we attempted to put together all of the data that were available and published for Earth as a stand-in for an exoplanet in preparation for Habitable Worlds Observatory. Running down the list here on the left are missions that I already mentioned. Mars Global Surveyor, as it was headed to Mars, took a look back at Earth and took a thermal emission spectrum. Again, HWO is operating in reflected light. So there aren't that many missions that have done this. And if you look at the phase angles that have been sampled here, there's a few at gibbous phases. So those are values below 90 degrees. There are many clustered around quadrature or 90 degrees, so half illuminated. And then there was one from the L-Cross mission that happened to capture a crescent phase view of our Earth. So especially crescent phase observations of our Earth are quite rare. Spectroscopically, I'm being a little bit misleading here with L-Cross because while the cameras on L-Cross could resolve the entire disk of Earth, the field of view for the spectrometer on board L-Cross was smaller than the disk of Earth. And so the spectra that we got from L-Cross are not full disk spectra of our planet. So sparse are the data that I can put them on a single plot that encapsulates all the information that we have for the phase and wavelength dependent brightness of our planet. I'm showing you here a quantity, my favorite albedo. If you don't have a favorite albedo, I hope that you pick a favorite albedo, and I hope that you join Team Apparent Albedo. And so this is an albedo that is normalized to a Lambert phase function. So a Lambert sphere Lambert surface reflects isotropically. And so this is a way of kind of using a Lambert phase function to correct for phase effects to try to put everything on a level playing field. And so there's Galileo photometry in black running through here from the 1990 and 92 flybys. There are data from NASA's Epoxy mission, which had 3 separate data sets, photometry in the visible, and then near-infrared spectroscopy out here in orange. And then I also put some L-Cross pointings on here, again reminding you that those aren't entire disk spectra for our planet. And so there are wavelength ranges, for example, here in the red to near-infrared where we don't even have spectra. And there are certainly phases that are not well represented. This standout here, this L-Cross spectrum that sits way above everything, has very high reflectivity because this was taken at kind of forward scattering geometry where clouds were scattering in the forward direction and a glint spot on Earth. So specular reflection off of the oceans was quite dominant in that image too, making Earth very reflective. So as promised in the talk title, this isn't just about Earth. There are a number of other worlds in our solar system that also don't have good spectral or phase-dependent coverage for their brightnesses. This is the best data set that we have for Jupiter. This came from the Cassini flyby with VIMS. We have similar data for Saturn that was taken during approach to Saturn with VIMS. You can see that we have a sampling here of about 6 phase angles. We do have good spectral coverage thanks to VIM, spanning the blue through the near infrared, which is where HWO would operate. And so there are also opportunities for other worlds in the solar system to have better data recorded here. Now, what I want to wrap up with is just noting that comparative planetology requires comparables. Exoplanet science has been advanced substantially by having comparison studies done to solar system worlds that help us understand these distant worlds where we generally don't have spatial resolution. When you have a mass of an exoplanet and maybe it's transiting, so you have a radius, you can put it on a mass radius diagram, and then you can put composition curves on there that are appropriate for the rocky worlds of our solar system or the gaseous worlds of our solar system to see if you understand the interior structure of that planet. When it comes to exoplanets, the few cases where we managed to detect species in their atmospheres, we can then try to understand if their metal enrichment in their atmosphere at their given mass is similar to what we see for, say, Uranus and Neptune in our solar system versus Jupiter or Saturn. And so I suspect that in the era of Habitable Worlds Observatory, where we're going to be recording the phase and wavelength dependent brightnesses of exoplanets in other systems, that we're going to generate data that I have faked here for you in gray that looks something like this. And one of the very first things that you're going to want to do is overplot phase curves for solar system worlds to try to understand if that planet is scattering in a way that is more like our Earth or more like Venus or more like Mars, or maybe you think you're observing a gas giant, so you'd want to put Jupiter or Saturn on this curve just to better place it within the realm of comparative planetology. So with that, I just want to highlight again that quality whole disk observations of solar system worlds that are spectroscopic are quite lacking and are going to be essential as both inputs to Habitable Worlds Observatory and to interpreting data from Habitable Worlds Observatory. And so why I wanted to come here and speak to you all today is that for in a planetary spacecraft or spacecraft headed to the moon during cruise phases of missions, these are inexpensive observations to make that have high scientific value for astrophysics. And so present an opportunity to have astrophysics relevance and astrophysics tie-ins to a diversity of missions that might have a spectrometer on board. And with that, I'll say thank you, and I'm happy to take any questions.
When you said there were 5 missions that had taken views of the Earth from far away to simulate what we'd see of an exoplanet, the 5 you picked were not the ones I expected. I thought you'd see Voyager or Pioneer or even from Cassini. And so is there a reason why none of those ever looked, they did look back. Why did we not get spectroscopy that would match?
Those data exist in the PDS, and I have students right now that are working on extracting those data. In the table that I highlighted, I made sure to put the word published in there because oftentimes these data are taken for kind of press release level science, but don't make it through to the publication stage. And that's fine. It goes into the PDS and can be analyzed later. But the problem that you run into, and this actually happens with OSIRIS-REx, and so I've spoken with Dante about this, is that when you have something like a gravitational assist and you turn your instruments on and you get full disk observations of Earth, for a lot of these spacecraft, they're operating in radiation environments, so brightness environments, where they weren't designed to be operating. This was true of the Galileo data. I have a student working on the Galileo data right now. It was designed to be operating at Jupiter, and where lower overall irradiances and fluxes. And so when you turn that instrument on or turn it towards Earth, there were a lot of saturated pixels, a lot of issues with saturation. And so if you have access to the instrument team who has the right kind of expertise to know where the instrument might be failing or to help you design your observations, that's really where this is best executed. And so for a lot of these missions that you might be thinking of, the instrument team or scientists on the mission didn't take it all the way through to a calibrated whole disk product for our planet that I could then put on a table like this. I do know that there aren't, I'm going to go out on a limb here. I don't think that there are great spectra of Earth in the wavelength ranges that I highlighted that are awaiting analysis in the PDS. I think that there's photometry in there, and I think there are useful things to do with the photometry, especially if you've got good phase coverage. But for spectra, I don't think that there's much more sitting in the PDS, or maybe anything more sitting in the PDS to pull out. Yes. Yep, and it doesn't have to just be Earth. It would be wonderful if we had a standardized set of these kinds of observations for as many solar system worlds as the spacecraft could access, because then it's all done with the same instrument. It's got the same resolving power. It's got the same wavelength coverage, and that would be a very useful and powerful data set. Epoxy kind of did this. It did it. Yes, and so we could talk a little bit more offline, but there are kind of gears are churning right there to try to make this happen. Thank you.